Very good evening, students.
Good evening, sir.
Good evening, sir.
Good evening.
All of you. So last class we have been discussing about tautomerism, right? So we'll complete that part and then go with the GOC2. So types of tautomerism, enol tautomerism, keto-enol tautomerism. We have discussed keto and enol forms. So where the CH2 minus will be going into the pi electrons to move away, and this will be the way your keto and enol they are going to be in the dynamic equilibrium with each other. Aldehydes and ketones having alpha hydrogens attached to sp3 alpha carbon shows this kind of tautomerism. Aldehydes and ketones having alpha hydrogens connected to sp3 alpha carbon, they will show this type of tautomerism, right? So which of the following shows tautomerism and which of the following will not show? A, B, C, D, 4 compounds have been given to you. Which will show tautomerism? All of you try to answer this.
B and C.
B.
So if you look at the conditions, so alpha hydrogen should be there. So this is the C double bond group. Alpha carbon itself is not there, so no alpha hydrogens. This is the C double bond group. This is the alpha carbon, so alpha hydrogens available. This is the C double bond group. Alpha carbons available, so alpha hydrogens are there. This is C double bond group. No alpha carbon. Alpha carbon is there, no alpha hydrogen. So obviously no tautomerism. So sp3 hybridized alpha carbon should be available. Along with that, hydrogen should be there, right? Which of the following compound does not show tautomerism? Which of the following compound do not show tautomerism? We have studied Brett's rule, right? What is Brett's rule? Can anyone say? Brett's rule we have studied or not studied?
No, sir.
No? So okay, fine. Solve this question first. Which of the following compound do not show tautomerism? Out of all the 4 compounds given to you, like A, B, C and D is all, which compound do not show tautomerism?
Sir, C.
A and B can show. A can show, like C double bond is a system. This is alpha carbon, this is alpha carbon, this alpha carbon is sp3 hybridized, it has alpha hydrogens, it can show. B, how it will show, Shuman? This is
Sir,
C
it's
double
called
bond.
gamma tautomerism, but I don't know how the mechanism is going.
Okay, so the gamma tautomerism is simply like this. So it is base catalyzed, right? So you have hydrogen available here. The base can actually pick up this proton. If base picks up this proton, you will be getting a negative charge developed here, and you will have C double bond like this. This negative charge can come into this C double bond system, can also move away. You will have negative charge here. Double bond positions have been shifted, and you have double bond O. Negative charge further comes into C double bond O, moves away. So you can have double bond positions in this manner, and O minus. This O minus will again try to pick up the proton from the base. So B will try to pick up the proton. Loss of base again, you will be generating phenol. Got it now, everyone? Even though you do not have alpha carbon which is sp2 alpha carbon which is sp2 hybridized, not sp3 hybridized, you can also have the respective hydrogen which can be in resonance with the alpha carbon. So conjugated hydrogens can also be involved. That is the point, and this is the mechanistic way. Okay, this is the mechanism way. So these hydrogens present here, they can also be in resonance with the just C double bond group in this fashion. So here you have hydrogens available, but in the third compound there are no hydrogens available even in the gamma carbon. So this compound will not show. So which of the following does not show tautomerism means C. C will be the right answer. C will be the right answer. That means it will not show tautomerism. Will not show tautomerism. Got it, everyone? Clear or not?
Yes.
Yes, sir.
Yes. Note, if directly attached alpha hydrogen is on sp2 carbon, then conjugate alpha hydrogen can also be transferred. This is alpha. This is also you can refer to alpha because it is conjugated. But here there are no alpha hydrogen. That means in practical you can say alpha, beta, gamma. So on the gamma carbon, if you have hydrogen which are in conjugation, that is also not possible. If you directly attach alpha hydrogen is on sp2 carbon, then conjugate alpha hydrogen can also be transferred. Which of the following compound shows tautomerism? Which of the following compound shows tautomerism? No sp3 alpha carbon and no conjugated alpha hydrogen. No alpha hydrogen. And in the compound C, you have the sp3 hybridized alpha carbon, and on that alpha carbon you have hydrogens. So compound C will be showing tautomerism. So answer is going to be C. Right? Try to solve this. Tautomer of CH3 C double bond O CH2 C double bond O OCH3 is. What was the tautomer? I can say C double bond O present here. With respect to the C double bond, I can write double bond here. So I can write this as CH double bond COH. With respect to the C double bond, I can write CH2 COH C double bond CH. With respect to the C double bond, I can write here also COH C double bond CH. CH double bond COH. CH2 double bond COH. This is possible. CH3 C double bond or CH double bond COH possible. CH3 COH C double bond CH. This is also possible. So how many cases are possible in total? All the three are possible or not?
Yes, sir.
So which is the right option? So right option is going to be
All
D
of
because all the three cases are going to be. The next type of tautomerism is nitroacenated tautomerism. So CH3 N double bond O NO nitro and acenato CH2 double bond N OHO. Same here, whatever the hydrogen we have here, CH2H N double bond O. This hydrogen is going to picked up by the base. So base picks up the hydrogen. So we get CH2, the CH electron density moves to carbon. So here we have this type of scenario, N double bond O. Negative charge comes into N double bond O, pi electron density moves away. So we have CH2 double bond N, NO minus NO. And now ultimately this molecule will try to pick up the proton from the base. Loss of base again, CH2 double bond N, OH, NO. Nitroalkanes containing at least one alpha hydrogen, they are soluble in alkali. Why? Because they are going to form respective NOH molecules. CH2 minus, this negative charge comes into N double bond of pi electron density moves away. So you get O minus. Okay, this is what the mechanistic approach is. Nitroalkanes containing at least one alpha hydrogen are soluble in alkali, aqueous NaOH, KOH, because on tautomerism they form acinitro form which reacts with NaOH resulting in the salt formation. Because whenever this compound is formed, CH2 double bond N OH NO, this OH bond can be broken because that is acidic proton is available and they can react with the base to form respective salts. Is that point clear to everyone or not? Nitroalkanes containing at least one alpha hydrogen, they are going to be soluble in alkali. Why? Because the base react with the acinitro form which is having acidic proton. Try to solve this question. Which of the following will be soluble in aqueous NaOH? Which of the following will be soluble in aqueous NaOH? This was a question.
A.
So you have to think of tautomerism, nitroalkane and acinitro form tautomerism you have to think. So alpha carbon should be available, sp3 hybridized, and alpha hydrogen should be present. Alpha hydrogen should be present. Alpha carbon should be sp3 hybridized, alpha hydrogen should be present. CH3NH2, CH3C, CH3, CH3NO2, C6H5NO2. So think of these cases. CH3NO2, CH3C, CH3, CH3NO2, C6H5NO2. So here you have alpha hydrogens, 3 alpha hydrogens. So it is soluble. Do you have any alpha hydrogens available here? No, not soluble.
No, sir.
Because this will be forming respective tautomer like this. CH2 double bond N, OH and O. So there is an acidic proton that will be reacting with NaOH. So salt is going to form. It reacts with NaOH to form respective salt. Whereas all these three, the remaining two are not going to be soluble in aqueous NaOH. Is that clear, students?
Yes,
Yes.
sir.
Yes. Nitroso-oxime tautomerism. Nitroso-oxime, CH3 N double bond O, CH2 NOH, same scenario, CH2H. So if you look at the if you look at the resonating structures, CH2H, N double bond O, base will try to pick up the proton. So base picks up the proton, loss of BH group. The CH electron density is given to carbon. You form CH2 minus N double bond O. Negative charge on carbon comes into N double bond O, pi electron density moves away. So you'll get CH2 double bond N O minus. This will again try to pick up the proton from the BH group. O minus picks up the proton, BH electron density is given to base. So you get CH2 double bond N. N is connected with OH plus B minus. So this is obtained, which is nothing but oxime. So nitroso-oxime, they will also have tautomerism. Amide imidol will also have tautomerism. CH3 C double bond NH2, CH3 COH double bond NH. This is amide bond. C double bond NH2 is amide group. C double bond NH COH, that is imidol group. Similarly, urea NH2 C double bond O NH2 and CH2, it should be NH2, right? NH2 C double bond NHOH. Same amide imidol, urea and the respective tautomer, all these are going to be produced. So these are the 4 kinds of tautomerism which we can have. Nitroso-oxime, amide imidol, yes or no? Nitro-acinitro, keto-enol forms. These are the respective tautomerizations which you can have. And using these tautomerization structures, we can think of whether a particular compound is going to be formed or not formed, whether tautomerism is possible or not possible. Is everything clear, students, so far?
Yes.
Yes, right. So enol content or percentage of enol content, these are important. First point is among keto and enol, which is more stable? Among keto and enol, which is more stable? Generally keto is more stable due to stronger C double bond O. The C double bond O bond is stronger. The carbon double bond oxygen, that is a stronger bond. Because of that, keto is going to be more stable. But now the comparison is not between keto and enol. The comparison is between enol content. So enol content stability, how to compare means you have to compare the stability of respective anion. The base picks up the proton. The CH electron is given to carbon. If that particular anion is resonance stabilized, if that particular anion is more stable, in that case you can say enol content is more. I am not comparing where enol content is high or keto content is high. I am comparing few compounds now. I am comparing the enol content of those compounds. After few sessions, we will be comparing the enol content with keto content. Generally, keto is more stable due to stronger C double bond O, but enol can also be more stable in case of aromaticity, extended conjugation, intramolecular hydrogen bonding. But now the comparison is not between keto and enol. The comparison is between the enol content of 2 different cases. Enol content stability you have to compare. Like greater the enol content means more stable the respective anion, that is acidic nature of alpha hydrogen. CH3 C double bond or CH3, and if you try to pick up this proton, you will get CH3 C double bond or CH2 minus. So you have to look at the stability of respective anions. If you take acetone, you are getting this particular enolate ion, like because negative charge can come into C double bond or pi electron as it moves away. What is this called as? Enolate. CH3 CO minus C double bond CH2. Okay, so you have to compare the stability of anion. If the anion is more stabilized, then the respective enol content is going to be high. Respective enol content will be high. In tautomerism, alpha hydrogen is transferred as proton. So if alpha hydrogen is more acidic, then more enolization means more percentage of enol or enol content will increase. That means whatever the alpha hydrogen we are picking out, if that is more acidic, then the respective anion which is formed, that is more stable, obviously. If the anion is more stable, then we can say enolization happened greatly. If enolization happened greatly, then we can say the percentage of enol is high. If enolization happened greatly, we can say the percentage of enol is high. Compare percentage of enol content. CH3 C double bond to CH3, CH3 C double bond to CH2, C double bond to CH3. So write the respective anions. In the first case, what is the enol you are getting? Like what is the anion you are getting? You will be getting CH3 C double bond O CH2 minus. In the second case, you will be getting what type of anion? CH3, C double bond O, CH minus, C double bond O, CH3. You may also argue, sir, here also we have alpha hydrogens. No. Why can't you pick up the proton? You can pick up. You can get another case like CH2 minus, C double bond O, CH2, C double bond O, CH3. Yes or no? These are the two respective anions which are getting. You compare now CH3, C double bond O, CH3, CH3, C double bond O, CH2, C double bond O, CH3. In the both cases, the respective anions are these. Of course, which anion is more stabilized? In the A1 or B1?
B1.
B.
B1, because the negative charge in resonance with two C double bond O groups, right? The negative charge is going to be in resonance with two C double bond O groups. So both sides resonance. So where the enol content is going to be high. So stability of anion is directly proportional to minus M effect. That is, electron withdrawing groups are more here. So more acidic hydrogen is present in the case B. So B is going to be more stable. So percentage of enol content is greater in B than in A. Is that clear to everyone or not?
Yes, sir.
Yes, sir.
Yes, right. Try to solve this question. Compare percentage of enol content A, B, C. Which will be high? So let us do the comparison. So we have to just remove the proton. So obviously, when compared to this terminal CH3, this CH bond, that is going to be more acidic. So you get negative charge here, negative charge here, negative charge here, negative charge here, negative charge on this particular carbon, and negative charge on this carbon. Look at now which is actually more stable. The negative charge is going to be in resonance, but a lone pair of electrons on oxygen, they were also involved in resonance. Yes or no? So if you look at CH3, C double bond O, so these are the negative charges. Negative charge, single bond, negative charge. From top to bottom, plus M effect of OCH3 increasing or not? Because lone pair of electrons on oxygen are present. So lone pair of electrons comes into the C double bond of pi electron and is moving away. So if a lone pair of electrons on oxygen are there from two sides, lone pair of electrons on oxygen only from one side in the second molecule, there is no lone pair of electrons on oxygen in resonance with C double bond O. Where is the negative charge on carbon is more stabilized? You try to understand. It is more stabilized in the first case or in the third case?
First case.
Because in the third case, already lone pair of electrons on oxygen comes into the C double bond of pi electron and moves away. So this C double bond of O minus system, that is going to be electron rich. So again, we have negative charge. If we are again providing electrons, that will be repelling. Electronic electron repulsion will be high. So when you go with 1, 2, 3, from up to down, plus M effect of OCH group increases. So stability of conjugate base decreases. So what is the percentage of enol content? So percentage of enol content will be A will be greater, then B, then C. Right answer. Okay, this is a percentage because lone pair of electrons on oxygen, they are also in resonance. Compare here, compare percentage of enol content in these cases. Which will be having more enol content and why? Which will be having more enol content and why? Compare, these are very simple questions. You can do it. Anyone? B, C, A, Suman says. Suman, just look at C once. So in compound B, you can easily say that you will be having this type of scenario, and this negative charge comes into C double bond of pi electron is to moves away, you will get phenoxide ion, which is going to be more stable, and we have generated aromatic nature. You look at C, in the compound C, if you try to pick up this particular proton, you get a C double bond O, negative charge comes into C double bond O pi electron and moves away. So it resembles like anti-aromatic system or not?
Yes. Yes, sir.
Because of anti-aromatic system, the destabilization is going to be very high. So whenever you have 4-membered rings, always think of anti-aromatic systems. There is a possibility of anti-aromatic. In compound A, you have generally negative charge here. Okay. So if you go with A, B, and C, so you will have respective cyclohexanol, whereas in B you have aromaticity, highly stable. In C, anti-aromatic. So B will be more stable than A, then C, because in C you have anti-aromatic nature. Okay, B will be more stable because aromaticity is gained. After B, if you think of just resonance, you will go with C, but C is actually anti-aromatic in nature, which is highly unstable. So after B you have A, and then after A you have C. That's the right answer. So this is how you have to compare the percentage of enol content whenever different molecules have been given to you. And comparison of keto enol content, like we have to now compare keto form and enol form, which will be having more percentage. In general, percentage of keto is greater when compared to percentage of enol due to strong C double bond O in keto form. Percentage of keto is greater when compared to percentage of enol. Why? Because of stronger C double bond O. But there are some cases where enol form is more stable when compared to keto form. What are those cases? But in some cases, percentage of enol may be greater than keto due to aromaticity, extended conjugation, intramolecular hydrogen bonding, extended resonance, and intramolecular hydrogen bonding. Compare keto and enol stability 1 and 2, whether keto is stable or enol is stable. This is your C double bond of keto form. This is your C double bond COH, enol form. Which is more stable among 1 and 2?
Enol.
Enol, because enol form is aromatic in nature. Keto is non-aromatic, so 2 should be greater than 1. You can say like that. Enol is aromatic, so enol should be greater when compared to keto. Generally, keto should be more stable because of C double bond O, but there are some cases where enol will be more stable because of aromatic nature or extended resonance, or aromatic nature or extended resonance, or intramolecular hydrogen bonding. Okay, 2 should be greater than 1. Compare here keto and enol. You can directly look at the molecule and say, right? Keto and enol, which is more stable?
Enol.
Why?
Because A is non-aromatic.
Okay, in enol form again aromatic nature is obtained, so enol is aromatic, so enol will be greater when compared to keto. Same logics. Before going into breadthrough, I'll give few more examples to try to solve this. Okay, for the compound given to you, enol form is more stable or keto form is more stable? For this compound, enol or keto is more stable. For this compound, keto form or enol form is more stable. Which one is more stable and why? Try to answer this.
Keto form is more stable.
Why, Faizan? Why keto form?
Because after losing H plus, there would be 4 pi electrons, which will make it anti-aromatic.
4 pi electron inside the ring only there? 4 pi electron should be inside the ring.
Yes, sir.
Inside the ring we have 4 pi electrons, C double bond O. Do you have 4 pi electrons inside the ring and planarity is there? CH2, CH2, CH2. No, right?
No, sir. No, sir.
Then, so if you try to write the respective enol form, you will have enol form in this fashion: C double bond O, C double bond COH. Now I think you got the idea.
Sir, hydrogen bonding.
Yeah, very good. So C double bond O partial negative one oxygen, partial positive one hydrogen. So what you can say? Intramolecular hydrogen bonding. So intramolecular hydrogen bonding is present. Due to intramolecular hydrogen bonding, this enol form is more stable. Okay, more stable. So what I can say, whenever you have two C double bond groups on adjacent carbon atoms, what you can say? In this case, intramolecular hydrogen bonding is possible. Because of intramolecular hydrogen bonding, the respective enol form is more stabilized. What about this case now? CH3, C double bond O, C double bond O, CH3. This is keto form. CH3, C double bond O, C double bond CH2, COH. This is enol form. Which is more stable?
Enol.
Enol or keto, and why?
Hydrogen bond.
Why the he says hydrogen bonding? Anyone else? Any other answers? CH3, C double bond O, C double bond O, CH3, that's keto form. CH3, C double bond O, COH, C double bond CH2. If you can think of, can I say partial negative is there on oxygen, partial positive is there on hydrogen? So can I say intermolecular hydrogen bonding is there or not?
Yes.
Yes. I'm saying enol is not stable now. Keto is more stable. Give the reasons. In this case, keto is more stable. Keto is more stable than enol. Why? Because whatever the carbon CH3, C double bond O, C double bond O, CH3 is there, CH3, C double bond O, C double bond O, CH3 will not exist in this fashion. Rather, the free rotation around carbon-carbon single bond will occur, because carbon-carbon single bonds are free to rotate. Because of free rotation, and the molecule will be existing in this manner: CH3, C double bond O, C double bond O, CH3. And if you try to write the respective, enol form, you will be having CH3, C double bond O, C double bond CH2OH. No intramolecular hydrogen bonding possible. No intramolecular hydrogen bonding. Okay, the CH3, C double bond O, C double bond O, CH3 will exist in this fashion, where the C double bond O groups will try to arrange themselves by a maximum distance. Why? Because to maintain minimum repulsions. Why it is happening? Because of free rotation around carbon-carbon single bond. So that is why keto will be more stable. So such enol forms are not stable because of high repulsions. The same logic we cannot apply to cyclohexane system, because you cannot rotate the carbon-carbon single bond in the cyclic system so that the C double bond will go into the ring. That is not possible, and we all know cyclohexane will exist in the chair form and board forms. Yes or no? So that type of rotation in the cyclohexane system, there is a possibility of intramolecular hydrogen bonding. But if two C double bond groups are on adjacent carbons in the acyclic system, then there is no possibility of intermolecular hydrogen bonding because of free rotation. Is that clear?
Yes, sir.
Yes, sir.
Okay. Let us proceed further, students. Next comes the Brett's rule. According to Brett's rule, planarity cannot be achieved at the bridgehead center. Bridgehead position cannot be sp2 hybridized in a bridgehead bicyclic compound unless one of the ring contains at least 8 carbon atoms. Like if you have these compounds are mostly common, right? CH2, CH2, C. This is nothing but your bridgehead center. This is nothing but your bridgehead center, because that is a bridgehead carbon which is connecting two rings or two cycles. So at this carbons, planarity can never be achieved. So these are your bridgehead centers, bridgehead carbon atoms. At those carbons, planarity can never be achieved. And that is why, if you think of any bicyclic system, you have to apply this Brett's rule. If Brett's rule is violated, then you cannot go with your general logics. So this application of Brett's rule is even important in the organic chemistry, like SN1 reactions, E1 reactions. Planarity can never be achieved means what? What you can understand with this logic? That means you can never form this part, you can never involve this carbon atom in the double bond. This is not possible. Yes or no? Understand these points carefully. You can never involve. That means we can never involve the bridgehead carbon, into double bond or carbocation or free radical. This is nothing but a Betz rule. Why it is so? Because of repulsions, the planarity can never be achieved. Because if they are in the same plane, the repulsions are high. According to Betz rule, planarity cannot be achieved at the bridgehead position in the bridged bicyclic compounds unless one of the rings contains at least H carbon atoms. Unless at least one of the ring contains H carbon atoms, we have to apply this rule to different sets now. So this position, so as I said, bridgehead carbon cannot have possessed positive charge. So sp2 bridgehead carbon ring does not exist. This type of ring will not exist. sp2 bridgehead carbon, because this is a bridgehead carbon which involved in double bond. Double bond means sp2 hybridization. sp2 hybridization means trigonal planar. So ring does not exist. Third case, ring will exist or not? Because this is the bridgehead carbon which is sp3 hybridized. This is also sp3 hybridized. Planarity is not there at the bridgehead carbon. So ring sp3 bridgehead carbon. So ring will exist. Are these logics clear to everyone?
Yes.
Okay, we cannot achieve planarity at the bridgehead carbon center. That is the point. So sp3 bridgehead carbon, for those carbons, ring sp3 bridgehead carbon rings will exist. sp2 hybridized bridgehead carbons will not exist. So that is how your bicyclic system would look like. That is how your bicyclic system would actually look like. Compare stability of carbocations. Which carbocation is more stable?
B.
You don't know Betz rule now. Now compare stability of carbocations. If you don't know Betz rule, you should say this is a carbocation which is connected to more number of alpha hydrogens. Like this is alpha carbon, this is alpha carbon, this is alpha carbon. It has 2 alpha hydrogen, it has 2 alpha hydrogen. In total, if you just try to compare, you have 6 alpha hydrogens. So you'll be having 7 hyperconjugative structures. Here you will have only 1 hydrogen here, 2 hydrogens here. So you have 3 alpha hydrogens only. If you don't know Betz rule, you will simply say A is more stable because of more number of hyperconjugative structures. But in reality, you can never achieve planarity at the bridgehead center. So what you can say is A violates Betz rule, but B do not violate Betz rule. So this compound B will exist. Compound A, that is carbocation A, will not exist due to Betz rule. Got it now? Betz rule is important because if you don't know Betz rule, you will be writing the positive charge at the bridgehead carbon and say it will have more number of alpha hydrogens and all, which is not possible because as the planarity is never achieved, we cannot have hyperconjugative structures also, because no bond resonance is also not possible because they are going out of the planes. Resonance is not happening. So stability order will be B greater than A. Try to compare now. What is the hybridization of nitrogen in the given structure? What is the hybridization of nitrogen in the given structure? Nitrogen has how many hydrogens? Nitrogen has how many bonds? How many sigma bonds?
3.
Like and lone pair, 3 sigma is there and 1 lone pair is there. So what you can say?
sp3.
sp3 hybridization. Can I involve the lone pair of electrons and nitrogen into pi bond?
No, sir.
Because again it violates Betz rule, right?
Yes.
Okay, I cannot involve the lone pair of electrons and nitrogen in Betz rule and say this type of molecule is formed. In that case, you will be having only 3 sigma. So this is not formed. Betz rule violated. Betz rule violated. So lone pair of electrons on nitrogen, they are present only on nitrogen or they are in resonance?
Only on nitrogen.
Only on nitrogen. So lone pair is localized due to Betz rule. So sp3 nitrogen, 3 sigma plus 1 lone pair, that means sp3 nitrogen. Compare here, in which of the following compounds hyperconjugation is possible? A and B.
B.
Because in A, if you think of here we have hydrogen, but we cannot involve that because we get a positive charge here. That is not possible. But in B, we have hydrogens available here. But hydrogens are not available in the A, that is sp3 hybridized carbon possessing alpha hydrogens. That is not possible in the compound A, because if that is going to be violating the Brett's rule. So no hyperconjugation due to Brett's rule, 2 alpha hydrogens possible. So obviously the second compound is going to be more stable, right? Tautomerism, again, as I have told you, we cannot have double bond at the Bridge center. Structure does not exist, because if you try to write the respective enol and keto form, this type of keto form is not going to be, this type of enol form is not going to be formed, because the bridgehead carbon is involved in the double bond. So this structure, is it possible? This structure will show tautomerism or not? Because you can also have this type of scenario, C double bond OH, possible. This type of structure, is that possible? It is also possible. Yes or no? Because here we have alpha hydrogens, right? Here we have hydrogens. So at the bridgehead carbon, it should not have plenarity. So the structures are possible here. That is compound 3 and 4. Like one, one is going to violate the Brett's rule. So structure does not exist. Whereas the second and third compounds, they can have sp3 alpha carbon has hydrogens. So they can be existing in the tautomeric forms. Which does not show tautomerism? Out of 1, 2, 3, 4. Out of these 4 structures, which will not show tautomerism? Will compound A show tautomerism?
Yes, sir.
Because this is alpha and conjugate hydrogens is available. Although alpha carbon is sp2 hybridized, the alpha carbon is actually in conjugation with the next NH bond hydrogen. Yes or no? So it can show, because you can have negative charge here. This negative charge comes into pi electron density, moves away. You can have negative charge on this position, C double bond O, double bond N. Negative charge comes into C double bond O, moves away. N, double bonds. Okay. So first compound will show. Second compound.
Yes, sir.
Yes, sir.
Second compound will show, because here we have hydrogens. Third compound.
No, sir.
Third compound cannot show, because bridgehead center violates Brett's rule. Fourth compound will show. Yes,
Yes,
or no?
sir.
Here we
Yes.
have hydrogens. So fourth compound can show. Bridgehead alpha hydrogen do not take place in tautomerism, so violates Brett's rule. So that is the third compound which will not be showing tautomerism. Okay. This is an example which you can understand. Right, students, this completes your GOC1. GOC1 is also called as reaction mechanism 1, which includes what type of bond cleavages you can have. Bond cleavages, heterolytic cleavage, homolytic cleavage, reagents, electrophiles, nucleophiles, intermediates, carbocations, carbanions, free radicals, carbenes, and different electronic effects, inductive effect, mesomeric effect or resonance effect, hyperconjugation, electromeric effect, acidity, basicity, SIR, steric inhibition of resonance, SIP, steric inhibition of protonation, ortho effect, tautomerism, Brett's rule. All these we have studied with a lot of examples. We have to practice this time to time. You have to remember all these rules, because these rules are only applicable in the upcoming chapters. Like whatever the organic chemistry I'm going to teach, all these inductive effects, all these electronic effects, and all these basics are going to be useful, right? So let us start with the organic 2, that is a reaction mechanism 2 or GOC2. So in the GOC2, you will be having reactions. What type of reactions means? Like you will be having nucleophilic substitution reactions, addition reactions, elimination reactions, and rearrangements. We'll discuss as many reactions as possible, and then we can go with the purification and all. Just a second. So how many types of organic reactions you all know? How many types of organic reactions you all know? Okay, organic reactions were classified into four main types. A, addition reactions. B, substitution reactions. C, elimination reactions. And D, rearrangements. So we'll discuss rearrangements. We'll be discussing generally under sets of reactions like rearrangements or isomerization reactions. So wherever you have the rearrangement or isomerization, those reactions we'll discuss. The set of reactions in D will be less. A, B, and C will be comprising more. So let us start with one by one. Addition reactions, substitution reactions, elimination reactions. We have to understand these reactions carefully here only. And I'm repeatedly saying what are the reactions we are going to study now. They are all overlapping in the upcoming chapters. Like after this, we'll start with hydrocarbons, alkyl halides, aryl halides, alcohol, phenol, ether, CHO groups, carbonyls, carboxylic acids. Whatever the reactions we study here, they are going to be overlapping in the upcoming chapters. So let us start with one by one. So first type of reactions is addition reactions. Addition reactions again classified into how many types?
Two
The
times.
first type, addition reactions are again classified into three types. Addition reactions are again classified. Addition reactions means the reagent is going to be added. Substitution means it is substituted. Elimination means elimination will happen. Addition reactions involves addition of reagent to the substrate and these are classified into three more types. Three types. What are those?
Nucleophilic addition, electrophilic addition,
Electrophilic addition, nucleophilic addition, and free radical addition. Electrophilic addition, nucleophilic addition, and free radical addition. Okay, first let us start with electrophilic addition reactions. Then we'll go with the nucleophilic addition, then with the free radical additions. So electrophilic addition reactions will be shown by many compounds. Generally, alkenes will undergo many types of electrophilic addition reactions. Why? Because alkenes have the pi electron density. The pi electron density is going to be attacking the electrophile first. In the alkene is already electron. It's because of the carbon-carbon pi electron density. That pi electron density of alkene will be attacking the electrophile first. Because the first attack is happening with the electrophile, that is why it is said to be electrophilic addition reaction. So let us start with the first case, electrophilic addition reactions. Electrophilic addition reactions. Alkenes generally undergo electrophilic additions. Alkenes generally undergoes electrophilic addition reactions, or EAR short form. Alkenes generally undergo electrophilic addition reactions because due to the attack of pi electron density of alkene to the electrophile in the first step. The pi electron density of alkene is going to be attacking the electrophile in the first step. So that is why alkenes are generally undergoing electrophilic addition reactions. Let us talk about different types of reactions of alkenes where they are classified as electrophilic addition. First type of reaction is addition of halogen acids. Halogen acids are what species? Halogen acids means what? HX. Let us take any alkene. Let us take an alkene and try to add the halogen acid HX to that particular alkene. Let us take a simple alkene CH3 CH double bond CH2 and we are trying to add HCl. What will happen in this scenario? In the first stage, can I say the pi electron density of CH double bond CH2 that is going to be attacking the electrophile. What is the electrophile in this scenario? HCl, the sigma electron density present between hydrogen and chlorine, that will be moving towards chlorine. Sigma electron density moving towards chlorine means developing partial negative on chlorine, partial positive on hydrogen. So can I say the pi electron density of alkene attacks the H plus? As soon as the pi electron density of alkene attacks H plus, there are two possibilities. You can generate a positive charge on the middle carbon or the terminal carbon. So which carbon generating or having positive charge is more stable? You can have two cases, CH3, CH plus, CH3, because this pi electron density attacking this particular H plus from this particular carbon, or CH3, CH2, CH2 plus. Out of these two, which is more stable, students?
First secondary.
Because secondary carbocation is more stable. This is secondary carbocation, this is primary carbocation. So now we can say earlier in the HCl molecule, hydrogen has partial positive charge only. Chlorine has partial negative only. But as soon as the pi electron density attacks, the partial positively charged hydrogen is connected to this terminal carbon, and the middle carbon, from the middle carbon, electron density moved away. So electron density moved away from this middle carbon atom. So that middle carbon atom is getting the positive charge, which is nothing but secondary carbocation. Secondary carbocation is more stable. And what happened to the chlorine? As soon as the electron density attack H plus, the hydrogen chlorine electron density that is given to chlorine now completely. So the chlorine which was present in HCl, that is now lost as chloride ion. And since the carbocation is formed as the intermediate, rearrangements or ring expansions are possible. Okay. So Cl minus, which is now present in the reaction mixture, that will now act as a nucleophile or not? Yes or no?
Yes, sir.
So
Yes,
Cl
sir.
minus is now going to attack this particular middle carbon atom, generating CH3, CHCl, CH3. What points you need to understand? First step is generation of carbocation. Carbocation is the rate determining step. RDS. And you can also say rearrangements of carbocation are possible. Rearrangements and ring expansion or compression is possible. Everyone got this? So the most stable carbocation is now going to be attacked by the nucleophile. It is not the least stable carbocation. Whatever the carbocation is obtained, that is going to be stabilized either by undergoing rearrangements. What type of rearrangements? Hydride shift, methyl shift, ethyl shift, they can occur. Ultimately, the nucleophile will go and attack the most stable carbocation. That is the mechanistic approach. Is that clear to everyone or not?
Yes,
Yes,
sir.
sir. Yes, sir.
So this is the simplest case. We'll now include one more different examples to understand. So example, CH3, CH3, CH2, Cl treated with HCl. What happens? I can write in this fashion or not? Sorry, I have taken alkyl halide, right? We have to take alkene, CH3, CH3, CH double bond CH2, HCl. So a solution goes like this. First step, the pi electron density is going to attack the electrophile. That is why this reaction is said to be electrophilic addition reactions. CH3, CH3, CH double bond CH2 treated with the H plus, partial positive on hydrogen, partial negative on chlorine, pi electron density attack H plus, will form CH3, CH3, CH, and CH2 is now connected with hydrogen, and this carbon will get a positive charge. This is only obtained. The positive charge is not going to be found on the terminal carbon because that is going to be 1 degree. So what type of carbocation is this?
Secondary carbocation.
Secondary carbocation, or you can simply say 2 degree carbocation. Now the secondary carbocation can undergo rearrangements or not? Is there a possibility to generate a more stable carbocation?
Yes.
Yes, sir.
Yes, because we have hydrogen available here. So that hydrogen, if you try to shift the CH electron density, if you try to do the 1, 2 hydrate shift, this 1, 2 does not mean the numbering. This 1, 2 hydrate shift indicates the hydrate has been shifted between two adjacent carbon atoms. You cannot do 1, 3 shifting. That is never possible. 1, 2 hydrate shift. 1, 2 hydrate shift occurs. As soon as the 1, 2 hydrate shift occurs, we'll generate this type of carbocation CH3, C plus CH3, CH2, CH3, which is nothing but your 3-degree carbocation. This 3-degree carbocation is now going to be attacked by the nucleophile. What is the nucleophile? As soon as the pi electron is attacked H plus, loss of chloride occurred. The chloride is now going to be act as a nucleophile. That nucleophile is now going to attack the electrophilic carbon, generating the major product like this. CH3, C, CH3, Cl, CH2, CH3, which is nothing but your major product. Everyone got this or not?
Yes, sir.
Yes.
Now let us do ring expansion. HBr or HI. And also if I take the same type of alkene and take HCl, HBr, HI, then if you look at the attack, the pi electron is attacking the H plus and the hydrogen iodine bond is going to be cleaved. Hydrogen halogen bond is going to be cleaved. So if you take the hydrogen halogen acid in such a way such that the hydrogen halogen bond is going to be cleaved easily, if the hydrogen halogen bond is cleaved easily, then that rate will be high. So if you take HI, iodine is very large in size, hydrogen is small in size. So that bond is going to be poor bond because of poor overlapping. So that bond can be cleaved easily. So this rate will be high when compared to HCl. So again same pi electron density attacks H plus. As soon as the pi electron density attacks H plus, what you will generate? You will generate a carbocation. This type of carbocation obtained. Yes or no? And loss of iodide ion, I minus is lost. Now we can say I can do one thing. What I can do is this is 2-degree carbocation. One possibility is I can think of I can think of more stable carbocation. So hydrogen is present here. I can do 1, 2 hydrate shift. If I do 1, 2 hydrate shift, what I will generate? If I do 1, 2 hydrate shift, I will be generating 3-degree carbocation, tertiary carbocation. When compared to secondary, tertiary carbocation is more stable. Can I now attack the iodide ion on this particular carbocation and say this is a major product?
No, sir. Ring expansion will be there.
No, sir.
Ring
Ring
expansion is
expansion.
possible. Why? What makes you say that ring expansion is going to be preferable when compared to the tertiary carbocation?
6-member ring are more stable.
Yeah, that's
That's
what,
why.
Suman. Why? Because of chair and chair forms. Okay. 6-member rings are more stable due to chair conformation. So that is why the 5-member ring, whenever it is there, it has to be converted to 6-member ring. So now we have two cases. Like whenever you are expanding the ring, you try to give numbering. So all of you all follow this approach only, so that whenever you give numbering, you get an idea. Once you write the 6-member ring, where to keep the substitutions, where to keep the positive charge and all. So numbering is not the IUPAC numbering. Numbering is just to given to those carbon atoms which are involving in ring. First carbon, second, third, fourth, fifth, sixth. Now I am writing the 6-member ring simply, and I am going to cleave the 2,6 bond or 2,3 bond. Here symmetry is there. Next case we will consider different example where I'll keep a substitution at a third carbon. So now as of now symmetrical case, so I can break either the 2,3 bond or the 2,6 bond. So 2,6 electron density is now broken and a new bond is formed between first and sixth. So this is first carbon, this is 6th carbon. First is connected to which carbon? First carbon connected to 6th. First carbon also connected to second. Second to third, third to fourth, fourth to fifth, fifth to sixth, sixth to first. So we got a 6-member ring. Now which carbon has what type of substitution? First look at substitutions. First carbon has methyl substitution. First carbon has methyl because first carbon is connected to methyl. That keeps that substitution is just keep it as it is. Which carbon has positive charge? First carbon earlier has positive charge. Yeah, first carbon earlier has positive charge. The positive charge on first carbon is nullified because the 2,6 electron density is given to first carbon. 6th carbon, earlier the 6th carbon is sharing the electron density with second. Now it is sharing the electron density with the first. So it has not seen any loss or any gain. Second carbon has seen the net loss in electron density or not? Yes or no?
Yes, sir.
So second carbon atom which has seen the net loss in electron density, that will be gaining a positive charge. first carbon which has seen the net gain in electron density, the positive charge on first carbon is nullified, and this is respect to your 6-membered ring. And now you can remove the numbering if you want. If you want, you can keep the numbering also, not an issue. 1, 2, 3, 4, 5, 6. So this is
So-
what type of? Yes, please.
So you said a second carbon has lost electron density. Why did you say
Yeah.
that?
Now, see, one chocolate is there. Second and sixth are sharing the one chocolate. Now, first and sixth are sharing the same chocolate. Okay. Understood this point or not? Second and sixth carbon atoms, they are sharing one chocolate, let us say. Second and sixth persons, they are sharing one chocolate. Now the chocolate is shared between first and sixth. What you can say?
It has lost electron.
First
Okay.
carbon is gaining the net chocolate or not? Earlier, I am getting half. Like if sixth person gets half, second person gets half. Now, the same chocolate is shared between first and sixth. Sixth person will get again half. First person will get half now. What about second person? Second person lost.
Yes, sir. Yes, sir.
Understood now or not? Now, instead of chocolate,
Yes.
you think of electron density. That's it. So, electron density shared between first and sixth means sixth has seen no loss, no gain. First has seen the gain. Second has seen the loss. So, whichever the carbon atom which has seen the net loss in electron density, that gets the positive charge. So, second carbon which has seen the net loss in electron density, that gets the positive charge. Positive charge on second carbon is what type of carbocation is this? Primary or secondary or tertiary? Positive secondary 2-degree carbocation, because the positive charge is present on a carbon which is connected to two other groups. Is there a possibility to generate more stable carbocation? Because we have hydrogen available here. We have to do hydrate shift or methyl shift.
Hydrate shift,
Why can't you shift methyl group?
because it will again generate 2-degree.
Very good. Because if I do the shift to the methyl group, again I will be getting a 2-degree. That is not happening at all. So 1,2 hydrate shift occurs. If 1,2 hydrate shift occurs, what you will be generating? You will be generating this type of intermediate. 6-membered ring, more stable carbocation, 3-degree carbocation. So this is the most stable carbocation obtained. Now the nucleophile comes into picture. I minus is the nucleophile. I minus attacks this particular carbon, generating this particular alkyl iodide. Got it?
Yes.
If I minus directly attacks this particular iodine, you will be getting, these are all the other options which can be given. So 5-membered ring only generating 3-degree carbocation, leading to the product, that is minor. 6-membered ring done the without doing hydrate shift. I minus attack the secondary carbocation, that is also minor. 6-membered ring where hydrate shift happened generated a more stable carbocation, that is going to be respect to major. Right. So now the question is, what happens if I include any methyl group here? The question now is, earlier we have a simplest case, now I have inserted a methyl group. What happens now? First case is same, Hi, pi electron is attacks H plus, partial positive on hydrogen, partial negative on iodine. So methyl group as it is, we get this type of carbocation, loss of hydride ion. I have to do the expansion of ring. But in the ring expansion, which bond I have to cleave? That is the issue. Because I have 5-membered ring, I can produce 6-membered ring. I can produce 6-membered ring. But which carbon atom I have to cleave? So let us give numbering 1, 2, 3, 4, 5, 6. Earlier, there is no substitution on third carbon. I can cleave 2, 3 or 2, 6, not an issue because symmetrical ring. Now 2, 3 bond, the third is connected to methyl group, the sixth is connected to no methyl group, only hydrogens are there. So which bond will be cleaved, 2, 3 or 2, 6? So let us leave 2, 6. So first, second and third. Second has positive charge. This first carbon and sixth carbon are connected. First is connected to second, second to third, third to fourth, fifth to sixth. So 2, 3, 2, 6 bond I have cleaved. Second carbon seen the net loss in electron density, so positive charge. First carbon seen gain, so neutral. Sixth carbon no loss, no gain, so as it is. I can also cleave 2, 3 bond. If I cleave 2, 3 bond, what I am getting? First carbon is now connected with a third carbon, third to fourth, fourth to fifth, fifth to sixth, sixth is connected to second. Where are the substitutions now? First carbon has methyl, Third carbon also has methyl. Which carbon would have positive charge now? Two six bond cleavage. 2,6 cleavage. 2,3 cleavage. Which carbon will get a positive charge now? 1,3 bond is now formed. 2,3 electron density is now shared between first and third. First carbon seen the gain in electron density. Third carbon no loss, no gain. Which carbon has seen the net loss in electron density in this 2,3 cleavage?
Second.
Second. So second get a positive charge. Now what type of carbocation is this? It is 2-degree carbocation. It is also 2-degree carbocation. Ring expansions. After ring expansion we get 2-degree. So there's a possibility of 3-degree. So I can do 1,2 hydrate shift. I cannot do methyl shift because I'll again generate 2-degree. So 1,2 hydrate shift if I do, I'll be generating this species. Now this is 3-degree carbocation. Now I minus can attack. I minus can attack, generating this product. Here it is 2-degree carbocation. This 2-degree carbocation again do hydrate shift. Of course 1,2 hydrate shift. So out of these two, which is going to the major and which is minor, you have to decide now. 2-degree to 3-degree. And in 3-degree, you can obtain again I minus is going to attack this particular carbon. We are getting different products, right? Yes or no? These two are different or same? Carbon 6-membered ring, methyl and iodine connected. To the adjacent carbon, we have methyl connected. 6-membered ring, methyl and iodine connected carbon, not to the adjacent carbon. After that, one more carbon is there to which methyl is connected. These are different. The point which you need to understand is ring expansion is not the rate determining step. What is the rate determining step? Rate determining step is the formation of carbocation. Rate determining step is the slowest step of the reaction. Which one is the slowest step of the reaction? Rate determining step is the slowest step. The other reactions, the other steps are going to be comparatively very fast. So ring expansion is not the rate determining step. So ring expansion is not the rate determining step means I can either cleave 2,6 bond or 2,3 bond. That bond cleavage occurs fastly. So you cannot decide which is going to major and which is going to minor because RDS is not the ring expansion. Write down that product here. Write down that content. Ring expansion is not the rate determining step. Or RDS. That means it occurs fastly. That means it occurs at a greater rate, which means both are possible. We cannot say which one is major and which one is minor in this case. Why? Because ring expansion is not the rate determining step. Is that point clear to everyone or not?
Yes, sir.
Okay. So such questions no one will ask. If they have asked, then what you should do? If they have asked, you have to go with the number of hyperconjugative structures. Like this is a 3-degree carbocation, this is also 3-degree carbocation. In the 3-degree carbocation, which structure has more number of hyperconjugative structures, that you have to decide and go with that. But ring expansion is not a rate determining step. So asking such questions is not valid. Right? Next example. Try to do this. HBr. What is the major part in this case? The pi electron, first step is the rate determining step. So pi electron is going to attack the H plus ion. As soon as the pi electron attacks the H plus, will generate what? We can have positive charge on this carbon or this carbon. Positive charge on this carbon is tertiary carbocation. So we'll have a carbocation like this. And as soon as the pi electron attacks partially positive hydrogen, loss of bromide ion occurs, loss of Br minus. So it is 6-membered ring already. It is already 6-membered ring. It is already 3-degree carbocation. So Br minus will directly attack or not? Br minus will directly attack, or is there any other conversions? Br minus will now try to directly attack. because it's already 6-member ring and already having tertiary carbocation. Is it going to the major product or minor product?
Minor
Minor. Why, Aishi?
repulsions.
Repulsions. Where do you have repulsions? Carbocations, 3-degree carbocations more stable due to hyperconjugated structures. Repulsions are there everywhere. Okay, 3-degree carbocations is more stable due to hyperconjugated structures. Repulsions are there in all the cases. So it is minor, that is true, but not due to repulsions and all. It is 3-degree carbocation, but if I try to do the hydrate shift, if I do 1,2 hydrate shift, 1,2 hydrate shift, I'll be generating one more compound which is again 3-degree carbocation. But what was the difference between these two? In this 3-degree carbocation, this is alpha hydrogen, this is alpha carbon, this is alpha carbon, this is alpha carbon. How many alpha hydrogens are there? 2 plus 2 plus 1. 5 alpha hydrogens are there. Here, 3 plus 3 plus 1. 7 alpha hydrogens are there. Even though we have both are 6-member ring, both are tertiary. If one tertiary to another tertiary, if there's an increase in the number of alpha hydrogens, there will be again the rearrangement possible. So 1,2 hydrate shift still occurs. You will be generating this stable carbocation because of more stable due to more number of hyperconjugated structures. More stable due to more number of hyperconjugated structures. So now this most stable carbocation is going to be attacked by the nucleophile. The nucleophile is bromide ion. So Br minus attacks this particular carbon, generating this compound, which is nothing but your major product. Everyone got it or not?
Yes, sir.
Yes.
Next, we'll look at other example where ring compression is involved. So let us take the 5-member ring, 7-member ring. So we have carbon-carbon pi electron exchange attack in this manner. It is the HCl. Pi electron attacks this particular hydrogen. As soon as the pi electron attacks, 1, 2, 3, 4, 5, 6, 7 carbons are there. As soon as the pi electron attacks, let us say positive charge is obtained here. Yes or no? 1, 2, 3, 4, 5, 6, 7, 7 carbons. This is a 7-carbon ring. 7 carbon rings are unstable when compared to 6 carbon rings. So ring compression can occur now. So let us give the numbering now. So 1, 2, 3, 4, 5, 6, 7. Again, ring compression is also not the rate determining step. I can cleave any bonds. I can connect the 1,2 bond and I can simply connect the first carbon atom. Or I can cleave the 2,3 bond. I can connect the third carbon to the first carbon. Or I can cleave the 6,7 bond. I can connect first carbon and 6th carbon. Both are happening at a greater rate. So no issue. Now I am cleaving the 2,3 bond and I am connecting the first and third carbons. Ring compression I am doing. Ring compression. So first what you have to do? You have to just form a 6-member ring. And now you have to just give numbering. So which carbons are connected to which carbon atoms? First carbon is connected to which carbon? First is connected to 7th, 7th to 6th, 6 to 5, 5 to 4, 4th is connected to 3rd, 3rd is connected directly first now. So what happened to 2,3 bond? 2,3 bond is cleaved. So third, yes or no? 3rd is directly connected to first, 2,3 bond is cleaved, and now first is connected to which carbon? First is connected to 2nd carbon, CH3. So now this is 2nd carbon. Which carbon will get a positive charge? Think logically and say. First carbon, 2nd carbon, 3rd carbon. 3 carbon atoms are there. Which carbon will get a positive charge?
Second.
So earlier the electron density is present between 2 and 3. Now it is present between 1 and 3. So 3rd carbon has not seen the net loss or net gain. Yes or no? Earlier the electron density is present between 2 and 3. Now it is present between 1 and 3. 2nd carbon has not seen the net loss or net. 3rd carbon has not seen the net loss or net gain. First carbon seen the gain. So first carbon will get a neutral now because earlier it has a positive charge. 3rd carbon no loss, no gain, but 2nd carbon has seen the net loss. 2nd carbon, since it has seen the net loss, it will have a positive charge. It is nothing but CH2 plus. Yes or no? What type of carbocation is this?
Primary.
Primary.
Carbocation. So primary carbocation can undergo
Hydrate shift.
Hydrate.
hydrate shift. So 1, 2 hydrate shift you can do. 1, 2 hydrate shift. So hydrogen is present on the first carbon. So 1, 2 hydrate shift if you do, you will be generating this type of compound. So after doing 1, 2 hydrate shift, you will be generating a 3-degree carbocation 6-member ring, more stable. So now Cl minus comes into picture. Cl minus, which is now acting as a nucleophile, it attacks this particular carbon. You will be generating 2 compound like this, which is nothing but your measure. And you all need to observe that the more stable carbocation you are producing, although you are producing the more stable carbocation is sp2 hybridized or not? Yes or no? Carbocation is sp2 hybridized. That means whatever the carbocation you are getting, that is having a trigonal planar geometry, trigonal planar shape. So the nucleophile can attack from the top or attack from the bottom. So you will be getting enantiomers. You will be getting what? Enantiomers. Is that clear? Nucleophile or halide ion can attack from the top or the bottom, of triangular plane, and thus we get enantiomers. Right. So these are the different cases where you can understand the addition of halogen acids to alkene system. Is that clear or not? Different examples we have considered: ring expansions, ring compressions, 3 degree to 3 degree, where increasing the number of hyperconjugate structure. Ring expansion is not the rate determining step. Right. All the cases we have discussed. Next, we can consider the second type of example is addition of halogens like X2 to alkene in non-polar solvent, non-polar organic solvent like, or non-polar solvent like CCl4 or CS2. CCl4 or CS2. Now the electrophile, whatever you are going to generate, that possesses a lone pair. Earlier the electrophile H plus ion do not have a lone pair. Addition of alkene to an addition, the pi electron density of alkene attack the H plus, which do not have lone pair earlier. Now the pi electron density of alkene is going to attack the carbon, attack the atom which possesses a lone pair of electron. How does that go? Let us understand now. Let us take an alkene like CH3, CH double bond CH2, and treat this alkene with halogen like Cl2 in the presence of a non-polar solvent like CCl4. So what is going to happen is you will get CH3, CHCl, CH2Cl. Okay, this is a reaction. This is a reaction, but you need to understand the mechanism. Mechanism is not applicable, not useful for all the types of reactions. But whatever the reactions I'm explaining the mechanism, you be perfect with them. Whatever the mechanisms I'm not saying, these are not useful of higher level. We have to remember what happens in this reaction and what are the conditions. Like oxidation reactions, we can say K2Cr2O7 with strong oxidizing agent, KMnO4 strong oxidizing agents. They will be oxidizing respective alcohols to carboxylic acids. Yes or no? In that case, you cannot study the mechanism because that includes greater than 10 steps. Okay. So whatever the mechanisms we are studying or I am explaining, be perfect with them. That has to be your first priority. Right, students? Mechanistic approach you try to think of. CH3, CH double bond CH2 plus Cl2 in the presence of CCl4, we form vicinal dihalides. You may ask a first question, sir, here where is the electrophile? Cl2 is a non-polar molecule. Earlier we have HCl, the sigma electron density present between hydrogen and chlorine, that is moving towards chlorine. But such movement is not available here because both are chlorine atoms. Both are chlorine atoms. Cl2 molecule is a non-polar molecule or not? Cl2 is a non-polar molecule. Both are chlorine atoms. Each chlorine will be having 3 lone pairs of electrons, and each chlorine will be having 3 lone pairs of electrons, and a chlorine-chlorine single bond is there. Now think of the attack. Cl2 molecule is a non-polar molecule on its own. That we have to agree. But Cl2 molecule is now in the presence of alkene. Alkene has a pi electron density. So at a moment of time, we can say the pi electron density is close towards one of the chlorine atom. The pi electron density of alkene may be closer towards one of the chlorine when compared to the other chlorine at a moment of time or at an instant of time. Can I say like that or not? Yes or no?
Yes,
Understand this point carefully. Cl2 is a non-polar molecule. The polarity in Cl2 is developed due to the presence of alkene. So it's a temporary effect or a permanent effect?
Temporary.
Temporary. So what type of electronic effect is happening here? Electromeric effect. Are you understanding? This is an electromeric effect happening. In the previous case also electromeric effect only. The pi electron density of alkane is attacking the electrophile whenever that electrophile is there. If there is no electrophile, there is no attack. So it is a temporary effect. So now imagine, let us say this chlorine is closer towards to the pi electron density. So pi electron density tries to attack this particular chlorine. As soon as this attack occurs, this chlorine sigma electron density will be given to chlorine to form a chloride ion. And now look at this chlorine. As soon as the pi electron density, let us give numbering. This is first carbon, this is A carbon, this is B carbon. Pi electron density attacking the chlorine through B carbon. So A carbon will get what charge?
Positive.
Positive charge. So but chlorine also has lone pair of electrons or not? Because
Yes,
of the
sir.
presence of lone pair of electrons, because of the presence of a lone pair of electrons, can I say the lone pair of electrons on chlorine will attack this particular carbon? So three steps are happening here. Three scenarios are happening. What are the three steps? Pi electron density of alkane attacking the chlorine. Why? Because that chlorine may be close at an instant of time. Why it is that as this chlorine is close, the sigma electron density is moving towards the other chlorine because the electron repulsions are there. As soon as the pi electron density attacks, this sigma electron density is given to other chlorine. So loss of chloride ion occurred. As soon as the electron density attacked to this terminal carbon, the center carbon which has partial positive charge, that will be again attacked by the lone pair of electrons on chlorine. So now we'll understand what is actually happening. Can I simply say chloride ion is lost? Chlorine sigma bond is there. That a sigma electron density is given to other chlorine, so chloride ion is lost. Chloride ion is lost. What happened to this terminal carbon and this middle one center carbon atom? CH3 double bond is now going to be converted to single bond because pi electron is attacked. And this terminal carbon is attacking the chlorine. This chlorine's lone pair is attacking the carbon again. Yes or no? 3-membered ring is formed. And do we have any charge on these carbon atoms? This carbon atom, like A carbon, B carbon, do we have any charge on A or any charge on B?
No, sir.
Because A and B have not seen the net loss or net gain. Yes or no? From the A carbon, electron density lost from this side, and electron density of A gained from other side. B also, whatever the electron density it gained, it attacked. So no loss in A or no loss in B. What about chlorine atom? The chlorine
Positive.
has 3 lone pairs. Now it will have only 2 lone pairs. And it will have a positive charge. Why it will have a positive charge? Because it has seen the gain from only from the pi electron density, but the sigma electron density lost as well as the lone pair lost. So it is nothing but a 3-membered halonium ion. 3-membered cyclic halonium ion is the intermediate, and intermediate is not the carbocation. So whenever we have a CH3, CH double bond CH2 attacking with Cl2 in the presence of non-polar solvent like CCl4, you will be getting a 3-membered cyclic halonium ion as the intermediate. That 3-membered cyclic halonium ion is not stable. It wants to undergo the ring cleavage because 3-membered rings are unstable due to electronic repulsions. Now look at this carbon chlorine bond. This electron density is moving. This electron density is also moving. So carbon chlorine bond electron density is moving towards chlorine to neutralize the positive charge on carbon. So this carbon has delta positive, this carbon also has delta positive. Delta positive on which carbon is more stable?
Middle.
A and B.
Second one.
A and B.
A.
A, because it resembles like a 2-degree carbocation. So now what happens? The chloride ion which is lost in the first step, that will now act as a nucleophile. It attacks the delta positive charge carbon. So this will happen in this case. CH3, CH, CH, Cl with 2 lone pairs and a positive charge. CH2, Cl minus, which is now present as a nucleophile, that will attack this particular carbon. This carbon chlorine electron density is given to chlorine. So chlorine will regain its lone pair or not? The chlorine will now regain its lone pair because 2 electrons present in the carbon chlorine bond, they were given to chlorine. So chlorine will regain its lone pair. So CH3, CHCl, CH2Cl is going to happen. And this attack is the chloride ion attacks in the anti-direction. Cl minus attacks in the back side or from the back side, from the back side of cyclic halonium ion to maintain minimum repulsions. To maintain minimum repulsions. Everyone understood this or not?
Yes, sir.
Yes, sir.
These are very interesting cases. Mechanisms are very interesting cases. You have to understand this carefully. So this is nothing but your mechanistic approach where you are getting respective dihalogenated compounds. So now the case is again, we have to go with the shortcut. I have given the shortcut to you, CAR, anytime earlier. Anyone remember the shortcut CAR?
Cis anti.
Gives, like if I take cis-alkene undergoing anti-addition,
R form.
will form racemic mixture. R means racemic mixture.
Yeah.
Okay, here I have taken propene. There is no cis and trans. But if I take butene, I can also have cis-butene. I can also have trans-butene. Addition of chlorine in the presence of CCl4 is undergoing anti-addition. So if I take cis-butene plus anti-addition will give racemic mixture. If I take trans-alkene, anti-addition,
Meso.
because cis-alkene anti-addition gives racemic means trans will give meso. Cis-alkene, syn addition,
Meso.
meso. Cis-alkene,
Trans, not cis.
yeah, trans-alkene, syn addition, right?
Syn addition. Yes,
Yeah.
sir.
Trans-alkene
mixture.
syn addition will give racemic mixture. Any examples of racemic syn additions? KMNO4 addition. Okay. Hydroxylation, we'll discuss that. Whenever you are trying to add KMNO4 to form ethylene glycol, or alkenes added with alkaline KMNO4 form ethylene glycol, that is syn addition, not anti-addition. So these shortcuts you have to remember. You cannot decide because it will be very lengthy. If you are to decide cis-alkene is forming racemic mixture or meso compound, it will take some 10 to 20 minutes, which you cannot do. We have to directly do cis-butene undergoing Cl2 in the presence of CCl4 forms what? If I frame a question, cis-butene undergoing reacting with Cl2 in the presence of CCl4 gives what? A, racemic mixture, B, meso compound, C, enantiomers, D, diastereomers. You have to go with cis-alkene undergoing anti-addition because Cl2 in the presence of CCl4 is anti-addition. So you will be getting racemic mixture. So like that you have to decide. Right, students, this is nothing but addition of Cl2 with a mechanistic approach. Let us look at different examples now. Example. So I have this type of compound now treated with Cl2 in the presence of CCl4. What is the major product? So Cl2, it will form what? Loss of chloride ion occurs. The pi electron density is now going to be forming a 3-membered halonium ion. So Cl will be having 2 lone pairs now and a positive charge. And this type of cyclic halonium ion is obtained or not? Now what you can take? Cl minus is now going to be attacking the carbon from the anti-direction. So it can attack this particular carbon. The carbon-chlorine bond is going to be used. So you'll have chlorine like this, and you will also have alkane in this fashion. Is it the major product or not?
Yes, sir.
Yes or no, all of you?
Yes, sir.
This is the minor product. Okay. Why? What happened? Because the first step is same. The cyclic halonium ion is going to be formed. But now the question is, the Cl minus will not directly go and attack this particular carbon, and carbon-chlorine bond is not going to be fluid because this particular carbon bearing partial positive charge is in resonance with the adjacent pi electron density. So resonance occurs. So this pi electron density is going to be involved in the resonance. Carbon-chlorine bond is fluid. So you'll be getting the terminal carbon attached with chlorine, and you have a double bond position shift, and this terminal carbon will get a positive charge now. And this will now be attacked by chloride ion to form this type of structure. Okay. So write down one point. In case of conjugated dienes, 1,4 addition occurs because earlier whatever the addition happened, that happened between two adjacent carbon atoms, that is 1,2 addition. In case of conjugated dienes, 1,4 addition occurs instead of 1,2 addition because the pi electron density is in resonance with the 1,4 addition occurs. Instead of 1,2 addition because of resonance of pi electron density of alkene with a cyclic halonium ion. Everyone understood this or not?
Yes.
Yes. Next example. What happens? What is the major part in this case? So you can think of this reaction. Attacking Cl2 produces what? Loss of chloride ion occurs. Cl2 in the presence of CCl4 means you have to form the 3-membered ring. So you will be getting the 3-membered ring in this fashion. 3-membered cyclic halonium ion is going to be formed in this fashion. The 3-membered cyclic halonium ion, whenever it is formed in this fashion, you should not write down this product. Cl minus, again it will attack from the back sides. So you cannot say Cl is here and Cl is here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is not your major product. This is a minor product. What happens in this case? In this case, the chloride ion is not going to be acting as a nucleophile. Why? The Cl minus cannot act this particular carbon directly. Rather, what happens means the nucleophilic oxygen which is present in the ring, that will now be acting as a nucleophile, forming a 6-membered ring. 1, 2, 3, 4, 5, 6. So lone pair of electrons and oxygen, they are going to be acting as a ring and they will be attacking this particular carbon. So let us try to do the expansion in such a way. So what will happen now? Oxygen. So if the acyclic compound itself has a nucleophilic atom, in that case 1,2 addition will not occur. Rather, the nucleophilic atom of the molecule will form a cyclic compound. Okay. So 1, 2, 3, 4, 1, 2, 3, 4, 5 and 6, and you have Cl with a positive charge, cyclic halonium ion. Give numbering 1, 2, 3, 4, 5 and 6. Lone pair of electrons and oxygen will attack which carbon now, 5th or 6th?
5th.
Because 6-membered ring is going to be formed. Oxygen is also going to be one of the atom in the ring. So we can simply say oxygen is present here. Oxygen is one of the atom. Oxygen is connected with OH bond. OH bond is as it is. Oxygen has 2 lone pairs earlier. Now it will have only 1 lone pair. Oxygen has seen the net loss in electron density, so oxygen will have a positive charge. Oxygen connected to first to second, second to third, third to fourth, fourth to fifth. 5th carbon, 5 and chlorine electron density is lost. 5th carbon is connected to which carbon? 6th carbon. 6th carbon is CH2. 6th is connected to Cl. The chloride ion which is lost in the first step, no. Here we have chloride ion lost, no. That chloride ion will try to pick up the proton now, and it will form ultimately this compound. Ultimately, this compound is formed, which is a major product. Okay, whenever the acyclic system itself has a nucleophilic atom and which can make the cyclic compound, either 5-membered or 6-membered rings are only formed, not the 4-membered, not the 7-membered. Only 5-membered and 6-membered rings can be formed in such cases, and you will not have same 1,2 addition, where rather cyclization occurs. Okay. So this is the addition of alkenes, addition of Cl2 in the presence of Cl4 to the alkenes. Tomorrow we will discuss more examples of addition reactions, elimination reactions, all types of reactions will cover. Okay, fine students, is that clear?
Yes, sir.
Thank
Yes,
you all.
sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.